run with and faster to run with.
They should put it up from back there. So whenever we're ready, we can see those slides. Perfect.
Oh, there we go.
Thank you so much. Yes, thank you for the introduction. My name is Thomas Eckert. We figured out all the issues here, and let me start taking you through this. Today, I want to show you how you can create Docker containers that are smaller, faster to ship, and more secure. Let's begin with a fairly normal looking Docker file to ship a Go web application. I can count myself among the people who've written a Docker file like this. We began with an Alpine Linux image that has Go 1.21 installed. Alpine is a distro of Linux that was designed to be lightweight. We copy the source code into the container, build the binary, and configure the image to export on port 8080, expose port 8080. On the final line, we instruct the container to execute the web app binary when it runs. So I took this Docker file and I used it to build an image for the code on the left. It's a simple HTTP server that only returns hello Gopher. When I build it, I get out an image that is 298 megabytes in size. It's not abnormal for a Docker image, but it's much larger than it needs to be. Because Go compiles down to a binary, when we want to ship an application, we don't need to ship an operating system to run it. The binaries we create can run directly against the kernel of the underlying host. So let's split the Docker file into two sections. The part that requires an operating system and the part that only requires the host kernel to run. We still want an operating system with Go installed when we are building the binary. But once that binary is built, we no longer need Go or the operating system. Docker has a built-in way to separate a Docker file into stages, where only the final stage becomes the output image. The first stage will still be based on Golang 121 Alpine, because we need an operating system with Go installed in order to build our binary. The final stage, where we only need the kernel, will be based on an image called Scratch, and we'll return to look at what that image is in a moment. First, let's see the effects that this has on our image. Using this Docker file, we get an image that is 6.72 megabytes, much smaller than what we had originally. And the new image runs just as well. Because the image is so small, pushing it to an image registry and pulling it down is much faster. You can even do it on conference Wi-Fi. Great, so what is Scratch and why else should we be using it? Scratch is an explicitly empty image, which signals to the build process that the next command in your Docker file is the first file system layer in your image. This means that what goes into your image is only the layers that you want in your Docker file, that you add in your Docker file, nothing else. In addition to being small, Scratch offers security benefits. Because the image does not contain an underlying operating system, a malicious actor cannot open a shell into your container and execute arbitrary code. Your images are also not subject to vulnerabilities that can be discovered in the operating system, at least at runtime. And you don't need to worry about keeping that operating system up to date. But you might just need this one thing in your image. Scratch might not be suitable for all use cases. And if it isn't, there are distroless images which differ from Scratch because they include CA certs, users and groups, temp directory, and time zone data. They can also include dependencies that you need to run your specific application. On the right, we have a GitHub repo with several distroless images for different runtimes and use cases. Let's review. We changed the Docker file on the left to the one on the right. As a result, we reduced the size of our image by 97%. We reduced attack vectors by removing a shell, and we made it so that we are only vulnerable to CVEs from the operating system at build time. I hope you can use this talk to write smaller, faster to ship, and more secure container images. Thank you.